Dear students, welcome to the second live session of the course Solar Energy Engineering and Technology. So before we start the discussion of some of the queries you might have, let us recapitulate the modules 6 through 9. Then we'll move to discussion of questions. Yeah. So in this session, we'll recapitulate the content of the module covered from 6 through 9. So in module 6, grid connected PV systems were discussed. In module 7, fundamentals of flat plate collectors were discussed. In module 8, flat plate collectors design and other aspects were covered. And in module 9, solar air heater principles and its working, then testing, all the information were discussed. So in module 6, lecture 1, we have covered functioning and layout of a grid connected PV system, then different components of a grid connected PV system, then selection of different equipment, and role of different components for maximization of PV system efficiency. Under the same module, in lecture 2, we are primarily discussing about design of grid connected PV systems. So the voltage, current and power rating of module and inverters are the three criteria which ensures a proper matching of the system in terms of performance and safety, which was discussed extensively, and design steps were discussed. Sizing of inverters based on the size of the arrays were discussed, and also demonstrated how to design a grid connected PV system. In the same module, in lecture 3, performance analysis of a grid connected PV systems were discussed, and we have systematically studied the performance analysis of a grid connected PV system, and also we have solved one numerical problems to determine the energy yield, specific yield, performance ratio, capacity utilization factor, and average system efficiency of a grid connected PV system. So also you can see this figure, the different components, like we have PV modules, then we need DC cables, then we need grid connected inverters, then AC cables, then AC load, then it will go to meter, and then finally we can provide energy to the grid. So if we have a net metering system, we can take energy from the grid as well. So in module 7, lecture 1, we have primarily discussed about the fundamentals of solar flat plate collector, its classification and different components like absorber plate, what is the material of construction, then what is the material of construction of tube, what is the tube diameter, header pipes, cover, insulation, collector box which has to be tilted at a suitable angle, and kind of fluid to be used based on the applications and location of installation. Sometimes we can use water, sometimes we can use mixture of water and ethylene glycol if the ambient temperature is less than 0 degrees C. Okay. Also, we have discussed the performance analysis of a flat plate collector, transmissivity estimation based on reflections, transmissivity estimation based on absorptions were discussed extensively. Also, we have learned the significance of transmissivity absorptivity product. And finally, we have studied the definition of instantaneous efficiency, how this instantaneous efficiency can be estimated or evaluated for a flat plate collector, and one of the very important parameter called stagnation temperature. We have studied the importance of stagnation temperature and how this stagnation temperature can be useful for design of a flat plate collector. And there was a question from the discussion forum that they could not see the variation of energy with respect to the wavelength of the long wave radiation when it is going back from the observer plate. So each variation is something like this. Okay, so maximum is appears at 10 micron. So I don't know what happened to the system, but sometimes it shows, but sometimes it is not visible. So its variation is something like that. Okay. And in module 7, lecture 2, we have studied the basics of heat transfer, because without analyzing or understanding the concept of modes of heat transfer like conduction, convection, radiation, it is very difficult to analyze the thermal system clearly. So this chapter was introduced to understand all the modes of heat transfer which can be applied for analysis of solar collectors. And also we have studied the non-dimensional numbers related with heat transfer, then correlations to estimate heat transfer coefficients, and also we have solved some basic heat transfer problems to strengthen the understanding of the system. In module 8, lecture 1, we have studied the collector losses and loss estimation. So what are different losses involved in the collectors, which has to be studied clearly, otherwise we cannot estimate the kind of losses taking place and our design will not be perfect. Okay, so these loss coefficients involve top loss, bottom loss, side loss, and if we combine all the three losses, what we will get, it's a overall loss coefficients. And also we have demonstrated the loss calculation associated with flat plate collectors, and it may be iterative techniques or it may be correlations. We can use correlations for estimation of this loss coefficient. So as you can see here, for loss coefficients, we need to consider QT, we need to consider QB, we need to consider QS. Okay, so heat loss from the collector will be something like QL is equal to UL multiplied by AP, then multiplied by TPM minus TA. So what is TPM? TPM is the average temperature of the observer plate, and TA is the temperature of the ambient air. Okay, and AP is the overall or area of the observer plate, and UL is the overall loss coefficient, right? And also we can develop the energy balance equation on the observer plate. So this is the observer plate and this is the glass cover. Okay, an amount of solar flux received by the observer plate can be calculated by using this expression. Okay, so that way we can do the entire analysis and we can calculate what is QL, which is sum of QT, UB, QB and QS. And one more thing I would like to clear to the students who has raised one point, like they have suffered a lot in calculating side loss. Okay, we have demonstrated how this top loss can be calculated, the bottom loss can be calculated, and side loss can be calculated. So here what happens if we consider this collector system, right? So this L1 is the say width and say length is L2 and height is H, right? So we will have faces like this face and then this face, and then we'll have this face and this face, right? So all the four faces we need to consider when we are considering the side losses. Okay, and then we have to consider the losses TPM to TA, that much of losses will take place, right? So when we are considering all these 4 directions losses are taking place, then we have to take the average losses. So that will be TPM minus TA. So that's how we have done the calculation here. So it will be QS is equal to, like we have, this is A, something like, if you recall this, our Fourier law of heat conduction, Q is equal to Ka dt by dx, right? So this K is for conductivity of the, or thermal conductivity of the insulation, and dx is the thickness of the insulation, right? So that's why ds is the thickness of the insulation and Ki is the thermal conductivity of the insulation. And then we'll have area. So how we have got this area? It is very, very clear. So we need to consider all the 4 faces. So this area will be L2 multiplied by H, and this area will be L1 multiplied by H. Okay. So there are 2 surfaces. This kind of 2 surfaces and this kind of 2 surfaces. That's why 2 is multiplied here. And then here delta S is delta S. But why 2 is here? Because we have considered average losses, TPM minus TA divided by 2. That's why this 2 contribution, this 2 is not for the 2 delta S. This contribution is from this concept. Okay. That's how when we apply here, then what we will get, US or loss coefficient will be L1 plus L2 multiplied by H into Ki divided by L1 L2 into delta S. So this is correct. For your understanding only, I have raised this issue here. And then in module 8 lecture 2, we have studied the flat plate collector designs and other aspects. Like we have started with energy balance of an absorber plate, then thermal resistance network, then temperature profile of an FPC. So if we consider this kind of 2 tubes, and then if we are interested about temperature profile, then what will happen, because heat will be carried away by the fluid, that's why this is a flat surface, and in between, so no contribution of cooling will be here to here and then here to here, but in between we'll have maximum temperature rise. Okay, so that's how we are interested sometimes about the temperature profile, and that way we can analyze the flat plate collector system. And then we have also included in the discussion about analysis of collector efficiency factor, then analysis of collector heat removal factor, then what is instantaneous efficiency, then what is series and parallel connection of the collectors. So these are the equations involved, and then what is collector efficiency factor, what is collector heat removal factor, these are defined just for your understanding how we have done the calculation. So QV is the useful heat gain, and this is the amount of solar flux absorbed in the absorber plate, and this is the amount of losses. And QL can be represented in terms of loss coefficient, which is nothing but overall loss coefficient, UL. And also we can simplify this equation, and we'll have 2 expressions for QU here and QU here, and this equation is known as Hotel-Wheeler-Bliss equation. Okay, so importance of this equation is quite significant, because this expression we can get the QU in terms of Fi. Okay, so normally this TFI. So this TFI is known to us. Okay, so if we know this TFI and TA is known to us, and then very quickly you can calculate what is the useful heat gain. Okay, and also we can express this FR, which is nothing but collector heat removal factor, which is mathematically expressed something like this. Okay, and FDES is nothing but collector efficiency factor, and its value varies from 0.8 to 0.95, and for FR, which is collector heat removal factor, its value varies from 0 to 1. And in module 8 and lecture 3, we have discussed about different factors influencing the performance of a flat plate collector. So what are those factors? Selective surfaces, number of covers, spacing, collector tilt, then dust on the cover, and also we have introduced the concept of evacuated tube collector. In the same module in lecture 4, we have discussed about testing of liquid flat plate collector, how a liquid flat plate collector can be tested, and also the applications of flat plate collector in swimming pools, water heating, milk pasteurization, power generation. Of course, that will be low power generation or low temperature power generation. Then drying, then solar power, solar water heater for biogas, slurry drying. Okay, and you can see here this is the system by which we can test a flat plate collector, and you can see the different components. These are reconditioning units, and then we need to perform the experiments at constant value of TFI and constant mass flow rate. Okay, so there's a distinction between the measurement or testing of liquid flat plate collector and solar air heater. So here, in case of liquid flat plate collector, we'll perform the experiments at constant mass flow rate and constant inlet fluid temperature. But in case of solar air heater, we have to perform the experiments at different mass flow rate to characterize the collectors. And in module 9, in lecture 1, basically we have introduced the fundamentals of solar air heaters, then performance of solar air heaters, and then what are different type of solar air heaters. In module 9, lecture 2, we have primarily discussed about solar air heater testing and then applications of solar air heaters. So application may be in drying of agricultural products. So we have learned drying characteristics curve, drying calculation, and process heat in industry, and solar air heater for power generation. So the figure what you can see here, this is similar to the testing what is adopted for liquid flat plate collector, but here we need to perform the experiments at different mass flow rates. Okay, because air side heat transfer coefficient is lower than liquid side heat transfer coefficient. So thank you very much for your attention. So now I'll now discuss the queries what you might have. Yeah, Saurabh Datta said about detailed assignment solutions are very much required. Of course, you will get it. Yeah, our TAs are involved in doing that. Already we have given the solutions. I think he will share it soon. Yeah, then PDF notes. Yeah, already we are sharing all the notes. Yeah, lecture notes will be shared to you all. Complete diploma in electrical engineering, industrial control, and 1-day solar course from NPTI. I don't know what is the question here. And there are some queries already I had. So how to study and which book? So this already is some of the information just shared with you through this discussion forum. Maybe we can share again for the study material. But what I suggest you please concentrate on the video lectures. What with you, I think that will give all the information, because this is a compilation of many books and many research papers. And then you have how it should be useful to us. That is, you can decide how this can be useful to you. So of course, this kind of course you will not get anywhere, which combines all the information starting from geometry. Then you have very very fundamental things about flat plate collectors. Then you have solar cells characterization, semiconductor physics, and then you will have power plant design, then energy storage. So almost every components are included in this course. Then one guy who is written what will be the exam pattern. Of course, it will be multiple choice pattern. And lots of formulas are being taught. Yeah, you don't have to remember the formulas. All the things will be there in the exam. And then pressure drop expression for solar air heater was given by 4FL rho V square by twice D, where D is the diameter, equivalent diameter of the duct, and what is the V? V is the velocity of air, which is represented in meter per second. So if you substitute no, in meter square, and if you do the dimensional analysis, then what you will get, it's a Newton per meter square. Okay, so it's correct. Then what is the difference if we calculate the losses of what is the difference in if we calculate the losses of PV panel? Your question is incomplete, so it's very difficult to answer what kind of question you are asking. So losses, of course, losses will be there, because as I said, so when you buy a solar module, so and if it is rated at say 200 watt peak, right? So that 200 watt peak you will get if the module is exposed to 1000 watt per meter square at 25 degrees C, and yeah, these two parameters are very important. Apart from that, you have to have this spectrum of 1.5. Okay, so under that condition you are expected to get 200 watt peak, but no, in actual practice this is not the case, because solar radiation will vary with time, and there are certain issues like manufacturing tolerances. Then dirt accumulation will be there on the top of the PV module, and the temperature, because ambient temperature will rise, and because of that, no, cell temperature or cell performance will degrade. Please discuss the final exam pattern. Already I said it's a multiple choice questions. How to acquire simulation with. So some of the things already you have explained in the videos. Please refer the videos critically. Then I think you will get all the solutions, like how to acquire synchronization of PV and grid voltage. So see, sometimes what happens, we cannot go very deep in electrical engineering. Okay, but what I am trying to give you in the modules, like how to connect it and how to design. So these informations are there. So if you want to learn more on electrical engineering, so please refer some electrical engineering books. Please explain the pressure drop equation in the duct of solar air heater. Also the various terms mentioned. So already I said about your delta P, and then it is dimensionally correct. But what kind of explanation you want, I'm not sure. How to acquire the synchronization of PV grid voltage achieved? Yeah. This is already I replied. So please, Saurabh Datta, please refer the class note. Sometimes you have to have some kind of your common sense. Okay, so how to design a system so you can apply your system. So Saurabh Datta, you have question assignments 9. Value of V, which is velocity of air, is not provided. Please post in the discussion forum, then we will provide you. And one of the students, he was asking about how to find the optimum inclination angle for FPC. This was very nicely elaborated in the video lecture. So please refer the video lecture. Narasimha Teja, yeah, thank you, Teja. So there is one question, how can we calculate thermal losses for PV panel as for FPC? So losses are there. So I think you have studied different things. I know when you study this module 12, there I have introduced one concept called photovoltaic thermal module. So there you can see this thermal losses, how this can be calculated. So if I ask a very question, see what happens normally if we consider say something like PV module, okay, what happens? There are different contact resistances, right? Say you have the different layers. So you have the glass cover, then you have a Tedlar, then you will have no PV cells, and then again Tedlar. So there are different layers, and then each layer they have some kind of thermal resistances. Okay, so that has to be accounted when we are doing no very accurate model. Okay, so there's a model, but practically it is very difficult to do it. But by using the modeling, we can do it. And please see that module 12. So there I have included some component of your things like thermal losses and how we can utilize both electrical and thermal energy from a single PV panel. Is it course question? The question is not so proper. Courses benefits in future. Of course, this course will be benefiting much because you will be master. If you read this course very carefully, you can know extend your research or extend your what is called company if you work in a company or maybe in that line. There are different dimensions of carry this study. Say for example, if you're interested to do something on solar photovoltaic thermal modules, then you will get the information about it. And if you want to apply some kind of knowledge about designing a flat plate collectors, then you can do it. Okay, and so different kind of instruments. Suppose if you're interested to develop some kind of instruments which is competitor of the existing pyranometer, okay, So that kind of instrument you can develop. Okay, so there are multiple benefits, and as a whole, if you read the system or read the course or so to follow the lectures very carefully, then I think you can learn many more things. Okay, like batteries are included. You can learn batteries. Okay, what kind of batteries, what new things you can do in batteries. So there are multiple dimensions of benefiting you by taking this course very essentially. Difference in if we calculate the losses for PV panel. Yeah, but as I said, this PVTs. Okay, so we can see how this can be calculated. Okay, like uh, PV panels are different. As I said, these losses are something like no manufacturing tolerances you need to consider, and then no. If you talk about this power plant as a whole, then cable losses, then we'll have no inverter inefficiencies, and then AC cable losses. Everything need to be considered. But thermal component, of course, thermal resistance is also offered at the contact points, so that need to be considered. Okay? Knowledge of heat transfer is again required for estimating precisely for solar PV panel as well. At the end of the course, so Shiva Teza, you have asked a question. Is there any possibility to discuss the numerical simulation boundary conditions to be given of solar collector thermal energy storage? I think I have solved some problems. When you get this module, I think we have discussed this in module 11. Yeah, module 11. Um, you yeah uh, already you have discussed. Okay. So how does a grid tied solar inverter big feature plus solar power? So there is a net metering system already. So that net metering system controls that the amount of solar energy you have generated that can be given to the grid, and an amount of energy which is taken from the grid. So when you are generating energy at the daytime, you can give it to the grid, and then when you need the energy, you can take it from the grid. So that net metering system take care of that. If you want to learn more electrical system, please refer some electrical engineering book, because this course is different than no core electrical engineering subjects. So Vinam Chaudhary, this is not the no, I think correct forum to discuss this. So Harish Khayani. So we have a paper published in Solar Energy about these thermal losses for PV panels. So you can download the paper and read it. So if you are really interested, then you can get a lot of information out of it. You just Google it, solar photovoltaic, and no, type my name, Pankaj Kalita. Then from that you can download the paper. So if you're facing difficulty, then you can email me. I'll send a soft copy of the paper, so you can read it. How we have calculated thermal losses in solar PV panels and PVT panels. So since there is no questions, then maybe we can close our live session here. So thank you very much for your questions and interactions. So see you in the next live session, which will be scheduled in the next month, maybe on 10th of December. Thank you very much.